Hey guys, hi, this is Radhakrishna. Welcome to my channel. I'm Krish. In this video, I'm going to be talking about function approximations, Fourier series, Fourier transforms, and stuff that leads up to Fourier transform. So this is a smart technique that comes out in almost each subject that you read. Now, it doesn't matter if it is biology, science, biotech, social sciences, economics, population dynamics, stock movement, right? Everywhere this frequency component or circles or something related to cos and sine is there. This is a technique that is going to come out there. So the basics of Fourier transforming, the motive of the Fourier transform or Fourier series comes from something that is called as function approximations or function fittings. Alright, so these days there's a lot of hype about artificial intelligence or machine learning or deep learning. What these techniques actually do is they take a set of variables and they create some sort of a function in their network or a model that they're trying to calculate, and put these variables through this model and try to calculate an outcome. May it be prediction, may it be classification, may it be saying, okay, this is the value that you were trying to calculate. So all of these techniques are also function approximation techniques or function fitting techniques in disguise. So Fourier transform or Fourier series are also something related to that. And one very good example is your heartbeat or any sensor that is actually put on your body. Okay, and if you intrinsically know that it's going to follow a function and the sensor is actually giving you data with respect to time. So I have drawn something here, but my drawing is very bad, don't mind. So I put a sensor on my body and it is giving some data with respect to time. So at time t0 I have this data, or I have the parameter, this parameter giving me some x value, and at time t1 I am having x0, and time t2 I am having x2 value, so on. I have a array of time and I have an array of signal values, and I want to find out how is the signal varying with respect to time, and what is this function that is actually following, right? So in such cases I apply some function approximations or function fitting techniques, and this is also something that I've drawn here. So if there is an AI method that is trying to detect your faces, what it does is it calculates some features of your faces and it tries to put those features into a sum model, and it will try to calculate some function which is actually correct. So it will try to learn that function, which is a function which will give your faces. So this is also a function approximation technique. So in such cases what happens is you try to find out a function which puts these values correctly according to what you need. So this is the basic function approximation or function fitting technique is a Taylor series. So what Taylor series tells is that if your function f of x is in this form of a power series, if your function can be expressed in terms of exponentials of a polynomial x power n's, then your function can be written like this. Your function f of x is equals to f of b plus the first derivative of f at b by 1 factorial into x minus b plus f second derivative of b by 2 factorial into x minus b whole square plus so on. So the general Taylor expansion is given like this. So any function which is limited, it can be expressed in this power series if you are able to calculate the derivative at any point b, right? So this is a important thing that you understand. So if you are able to calculate the derivative of the function, nth derivative of the function at a point x is equals to b, then you are able to calculate your f of x. Alright, so there are some really good techniques where you can computationally calculate the derivatives, or there are some cases where you can calculate the derivatives but you cannot actually calculate the function itself. So there, in those cases, you actually apply this Fourier series or Taylor series in order to calculate the function f of x. Now if you are trying to calculate the function sine of x using Taylor series, this is the expansion that you get, because you know the nth derivative and my b is actually 0. If I put b 0 and if I put my nth derivatives of sine x and calculate sine x, I'm getting x minus x cubed by 3 factorial plus x power 5 by 5 factorial and so on and so forth. If I'm taking cos x, I get this expansion. If I take e power x, I get this expansion of 1 plus x by 1 factorial plus x square by 2 factorial. Most of you might be knowing this, some of you might not be knowing this. If you are interested in this, I encourage you to calculate the nth derivative and calculate this function at b is equals to 0 for all sin x, cos x and e power x. And the famous Euler's formula of e power I theta is cos theta plus I sin theta can actually be calculated by substituting these particular Taylor series expansions into this thing. So you calculate the LHS, you calculate the RHS, and they both will turn out to be same. So this is how Euler had done that formula of e power I theta cos theta plus I sin theta. So this is brief interview or brief introduction about Taylor series, and now we'll jump right into Fourier series. So now that you've understood how a function can actually be approximated using some polynomials, Fourier series brings a concept of approximating the function with respect to some sinusoidal or cosine waves with different frequencies. Alright, so I have put here a basic representation of the sine and cosine waves. Let me just show that to you so that you can understand it. So what I have done here is I have taken some cosine waves. I've just plotted some various frequencies of cosine waves. The blue wave is cos theta, so it touches 0 at pi by 2 and is minus 1 at pi, so on and so forth. So you can see the red wave or the cos 2 theta wave is actually having much more frequency than the cos theta. So Fourier series brings us to a view of summing up these waves to approximate a function. Alright, so what I did here is I added cos 2 theta plus cos theta, and I have got this green function. And similarly what I did is I have added cos 2 theta plus cos 3 theta plus cos 4 theta, so on, cos 20 theta. So I got this function. If my given function was this green signal, how I do my Fourier series is by writing that this function is a summation of cos 2 theta plus cos 3 theta, so on, like cos 20 theta. So this is an abstract view of a Fourier series. So I did cos 2 theta plus cos 3 theta plus so on, like cos 200 theta. So there are 200 waves that are summed up in this, and so you see 3 peaks. So if your given input was a function that is similar to this, then your Fourier series will be from 2 to 200 of cos. And similarly, this is a random weight multiplied by cos 2 theta, cos 3 theta. For each of the waves, I have multiplied a random weight and I have got this. Alright, so this is something that introduces you to the summation of various causes and cosine or sinusoidal waves. Right, so any function can be approximated or given as a summation of those nth component or nth frequencies of cosine waves and sine waves. And this Fourier series is also very useful for predicting or this approximating periodic functions. So this summation you can write within a cycle. Alright, so if your function is like this, what you do is it is periodic from 0 to t and again 2t, you get a 3t here. So you take one cycle and then you define it like this, and then it is going to be automatically generated for all of these things again, because you're already using your other periodic waves. Alright, so this particular expression has a period of 2 pi because the major functions of cos and sine are having a period of 2 pi. Now if you want to do for a function for 0 to t, you have to squeeze your x-axis inside your cos and sine, and you generate this thing for 0 to t. So what you can see below is a general expression of a Fourier series for any function 0 to t, capital T. Like if the function is given to you with from 0 to capital T, you can express it like this, and after capital T it is going to repeat again. For example, if your function is like this from 0 to t, again from 0 to t, again your function is going to be like this, again and again it's going to be repeat. So it's going to be a periodic with a period of capital T, right? So how do you find out the weights, as if you found those weights of this x minus b whole power n in Taylor series as f nth derivative by n factorial. In Fourier series, you do a small calculation. So what you do is, for this f of x, you multiply cos of 2 pi by t mx and you integrate it from 0 to t on dx. And what happens is, this cos goes here, cos goes here, and cos goes here. And by using some trigonometric identities, you can make this one to 0, this one to 0, and if the cos is there, then only one value is going to remain, then that is for cos mx. Whatever frequency you multiplied the function to, only that value is going to remain, and it's going to give a value of t by 2 pi into pi. So your am, basically your weight, and this integration is actually very simple. I encourage you all to try it out. So your weight am, or the weight of the cos wave for mth frequency, is going to be 2 by t into this integral that you did, and the sine weight is going to be 2 by t into integral of into multiplied by sine. So this is the actual Fourier series that everyone talks about. This is the continual Fourier series. Alright, and the m is the frequency, the sine mx wave, sine cos mx wave, and the t is the period of the function. Now one more understanding of this Fourier series arises from the expression of cos theta and sin theta as e power I theta. So the thing is, if you're able to see cos and sine somewhere, you can express cos as a sine and sine as a cos with a phase difference. So you can express this Fourier series also as something like this: a naught by 2 plus summation over capital AN, which is not exactly similar to AN, with cos of 2 pi nx by t minus some phase. Alright, so if I'm trying to expand this particular function, what I get is cos a minus b, which is cos a cos b plus sin a sin b, and I'm trying to expand with an, and I'm trying to do a summation also. So what I am able to see from here is that it almost resembles this. This almost resembles this. So I have an cos plus bn sin. What I have here is a capital An cos phi into cos plus capital An sin phi into sin. What if my capital An sin phi of sin is actually bn and my capital An cos phi is actually an? So I can equate both of these representations. So I will try to find out a capital An and a capital phi n such that they satisfy this thing. So if I'm trying to find that out, I'm getting an, capital An, as root of an square plus bn square. This is normally solving a trigonometric identity here. Just square sine square plus cos square equal to 1, and then you divide them and you get phi n equal to tan inverse bn by an. Alright, so with this set of an comma phi, you can represent this Fourier series that you know ans and bns for as this: a naught by 2 plus summation over an cos of something minus phi. Right, now it's important to understand that you can also express this is n equal to 1 to n as an log of n equal to minus n to n cn into e power I theta. Alright, so this over here, this f over x, which I am giving as minus n to capital N cn into e power I 2 pi n x by t, is the actual Fourier series complex representation that everyone talks about. Alright, this is the Fourier series, the continual Fourier series, and an log of e power I theta. So I did this from here. So if I am able to represent cos theta in the terms of the complex conjugates, it's going to be e power I theta plus e power minus I theta by 2. Alright, and this minus I will just go from minus n to n. So there is this complex conjugate. It is also easy to actually comprehend. So when you put this over here, so the theta will be 2 pi nx minus phi n, and here minus of this theta. And if my n ranges from 1 to infinity, you have to write it like this, but if my n ranges from minus n to n, I can actually put those complex conjugates together and I can write it like this. And this is also true for complex valued functions of f of x. If my f of x is actually returning some complex numbers, my Fourier series can also be represented like this. So this equation is actually a generalistic Fourier series representation in the complex form. Fourier representation in the complex form. Now the Fourier series values, or the weights Cn, is actually the same values of that you've got here. It's almost similar to these values, right? So you have a period from 0 to capital T, and then I have my f of x, it's my function, and what I do is I do e power minus I 2 pi n, and then my range value by the time period dx. Alright, so this is Cn, which will give you my weights for Fourier series. So all of this, what you're seeing here, is a continuous domain. So my x is actually continuous. Okay, so what happens if my x is discrete? So I cannot do a integration, I have to do a differentiation. So the analog in the discrete world, the analog, I mean the synonymous function, because when I talk about analog, you can confuse between discrete and analog. So my synonymous function of this particular transforming a normal wave into its frequency domains xk is going to be a summation over my n going from 0 to n minus 1 xn into e power minus I 2 pi k capital N by this. Alright, so this over here is the transformation that transforms a given set of a time series signal into its frequency domain components, and this is called as a discrete Fourier transform. Okay, so if this is something that you can understand or digest, it is, I think, mostly easy when you see the analog from this to here, but if you're not able to, I'll explain this in a practical way. Now there is also something called as inverse discrete Fourier transform, which what it does is xn is equals to 1 by capital N into n is equals to 0 to n minus 1. You take xa into e power I 2 pi k n by n, and what you're doing here is you're actually transforming the frequency domain into time series, and that is why it is inverse. So normal forward Fourier transform, what it does, it takes time series, converts into frequencies. Inverse Fourier transform takes frequencies and converts into time series. Now how this is applied, let's talk about that, because that is actually important. Okay, and maybe you will understand more here. So my n is equals to 0 to n minus 1 xn into e power minus I 2 pi k small n by capital N. This is the Fourier transform that I've got. So if I have a signal with 4 samples, 0 1 2 3, so these are 4 samples I have got some values, 1, maybe 2, maybe 1 again, and maybe 4 now. So I have got the signal 1 2 1 4. So how many n, capital N here, capital N is equals to 0 1 2 3, so I've got 4 samples. Okay, and my xk is going to be like this. So it's a summation of x0 where n equal to 0 into e power minus I 2 pi n equals to 0 by capital N going to be 4 into k. Alright, plus same thing x1 into same thing n equals to 1, so e power minus I 2 pi 1 by 4 into k plus x2 into e power minus I 2 pi 2 by 4 into k plus so on. So there's one more term, let me write it out. So 2 pi 3k by 4. So here x1, x2, x3 and x4, they are 1 2 and 1 2 1 4. This is the signal terms, right? So if I put approximately them over here, I have what? So this is e power 0, isn't it? So this is 0. So 0 into anything is 0. E power 0 is going to be 1 and x0 is 1. So I have 1. plus what is x1? x1 is 2, so 2 into e power minus pi k by 2. Alright, plus x2 is 1 again, and I have what? E power minus I pi k, plus what is x3? x3 is 4 into e power minus what I have here is 3 pi by 2k, and my k, this is xk. Okay, so my k again can range from the n equals to 0 to n equal to n minus 1. So my again k is equal to 0, 1, 2, 3, because I have 4 samples. My n actually is time 0, 1, 2, 3 time. These are the time samples. So accordingly I have put n equal to 0, 1, 2, 3. I have summation over that, and I have a k. So I have a k again, also same thing. So if I want to find out what is the frequency, first term of the frequency, x, capital X is 0, I just put k is equals to what? 0. So I get 1 plus 2 power, so k equals to 0 everywhere. It's going to be 1, 1, 1, 1. So I have x plus 4. So this is my k equals to 0. If I have a k equals to 1, I have 1 plus 2 into e power minus I pi plus k equals to 1. So again I have no, pi by 2, this is, because this is a k pi by 2. I have e power minus I pi plus 4 into e power minus I 3 pi by 2. Alright, so similarly you will get for x2 and x3, and these are also easy to solve. This is nothing but cos pi by 2, and this is e power I theta, right? So this is cos minus pi by 2 plus I into sine of minus pi by 2, and cos minus pi by 2 is 0. Right, yeah, so this is 0, and this is minus I. So all of this is just going to be minus I. So I'll just do this. 1 minus I plus e power minus I pi, sine is going to be 0, and cos is going to be cos pi. Cos pi is actually minus 1, 0 pi by 2, 3 pi by 2 minus 1, yeah, minus 1. So, and it's a minus, so cos of minus theta cos theta. So this is going to be what? It's going to be minus 1. Alright, this is just going to be minus 1. Plus again you have 3 pi by 2, you can solve that. So you'll have some value, complex value. So you have an x1, you have an x2, you have an x3. So what you have is an array of frequency domain values, x1, x2, x3. So what you did, you converted your signal of, or what was your signal? 1214, right? So what you did is actually you converted 1214 into frequency domain. So this is actually the discrete Fourier transform that people actually talk about, and there are algorithms like fast Fourier transform which can actually do things of this transformation is very fast. So this, what this will be able to help you is, this will help you in finding out the frequencies of your signals, and maybe you want to do some frequency domain processing, maybe in some image processing, and there are lots of other applications that you can do on frequencies, and then you can again get back your time signal by doing a inverse discrete Fourier transform, and you will have the time signal back again after your processing. But if you don't want to do that, if you want to just visualize your time series signal in a frequency domain, all you do is a DFT. So that's it for this video. I hope you have understood, or maybe just got a gist of the Fourier series, Fourier transforms, and the function approximations. So any signal given, you can fit it to a function. If you're doing it for cos and sine waves, it is Fourier series. If you're doing it with power series, it's Taylor series expansion. And if you're doing it with some simple linear algebra, it's called as neural network. So that's it for this video. If you like this video, please share it with your friends, and also subscribe to my channel. Some more stuff is going to come which will maybe interest you, because I'm doing this series where some topics which have changed the landscape of science on Earth. So this was the second of that. The first was about Kepler's laws, and the next thing is actually pretty interesting. I like the next subject very much. So if you want to know what is it, please tune to my channel in the next video. Meet you in my next video, guys. Goodbye.